The LG Procast, the podcast, is intended for informational and entertainment purposes only. The views or opinions expressed by the podcast hosts and guests do not necessarily reflect the official position of LG. For the latest and most accurate information about LG products, please consult relevant product manuals and related documentation. The information provided in this podcast episode is for informational purposes only and does not constitute professional advice. While we strive to provide accurate and up-to-date information, we make no representation or warranties of any kind, express or implied, about the completeness, accuracy, reliability, or suitability of the information for any specific application in the following discussion. LG and those posting or otherwise providing information, content, or material are not responsible or liable for any consequences relating directly or indirectly to any action or inaction you take based on the information, content, or other material on the podcast.
Welcome to the LG Procast. I'm Phillip Kriegbaum.
And I'm Terry Frisenda. Welcome to today's episode. We have very pleased to have a guest on today, Mr. Ross Trethewey. Ross, tell us a little bit about who you are and what you do for a living.
Well, yeah, I'm a mechanical engineer. So I design and consult on mechanical systems. You know, we're based in Boston, Massachusetts. The company I run is called TE2 Engineering. I'm also the building engineer on the television show This Old House and Ask This Old House. So we're trying to bring some of that new technology, kind of bring it to the TV screen to try to, get the education and the consumer awareness up on these projects and on the products that we're talking about.
Awesome.
Thanks for joining us. Today, we want to pick your brain a little bit about air-to-water heat pumps.
Yeah, I love them.
So with the new A2L refrigerants and, all the noise that was around that and flammability, LG's air-to-water heat pump is self-contained. Refrigerant stays outside the home, which has probably got some positive benefits for those in that area. But bring us up to speed as much as we can in a half hour. Ross, what are we talking about?
Well, first off, air-to-water heat pumps is nothing new, right? So a lot of people have heard chillers before. These are just reverse cycle chillers, right? So they've been used commercially for many, many years. They've been used in Europe for many years. When I lived in Germany, this was a very, very common way that, those types of countries heated and cooled buildings. It's heating first, air conditioning second. A lot of parts of the United States a little bit different with the way they're set up with air conditioning dominant versus heating dominant. But at the end of the day, an air-to-water heat pump effectively is an outdoor box in the package monoblock style is what we call it, where it's got a self-contained refrigeration circuit inside of the system. And it's designed to provide hot water, heated water, or chilled water, cool water, at really all different times of the year. So when you need heating, even at minus 13, these air-to-water heat pumps can deliver, very, very high temperatures. And then on the flip side, obviously, it could be 110 degrees outside, and these things can produce, 41, 42 degree chilled water. And so that's the magic of what an air-to-water heat pump does. Magic box outside that heats and cools the buildings with hydronics.
Interesting.
So for the guys who don't really have a hydronics background, myself, worked in the South and really never got into hydronics as part of my career. Once the cold water, the hot water comes into the home, what are most contractors doing with it? How are they using that to heat or cool the home?
Yeah. So a part of it's application specific. So are we heating dominant? Are we cooling dominant? And are we going to have times where we need simultaneous heating and cooling? But at the end of the day, most of these systems are set up with a hot tank. And so there's a buffer tank. And the reason you need a buffer tank is with hydronics, you want that air-to-water heat pump to be able to run long durations, not short cycle, right? The analogy I give is with like a car, right? You're not going to turn your car on and off, on or off, on or off. You like to let it and set it for cruise control. So a lot of times the load inside the building is variable, right? It's changing all the time. So you have this inverter compressor outdoor unit that produces that hot water or that chill water. You want it to run that long cycle to match up with the heating load or the cooling load, depending on what mode we're in of that building. And a lot of times you have an accumulator or a buffer tank to basically bridge the gap between the differences in terms of capacity of what the unit can provide and what the load is on that building at that moment in time. And another analogy I give is that if you had a small room that was calling for heating and it was the only room in the house that was calling for heating, the load might actually be quite small. And so if you had a large heat pump, let's say a 5-ton heat pump outside, even though it can vary up and down with capacity, it's not going to throttle down small enough and low enough in load to meet the loads of that room by itself. So the volume of the system becomes that buffer to allow it to run for long cycles, at least 5 minutes, ideally 10 minutes of runtime, so that you can let that system get to cruise control and actually give you the efficiency that it deserves, right? Because if you short cycle these units, not only is it bad for the mechanical wear and tear on the equipment, but on the flip side, you never reach the efficiencies that the system is really designed for, right? You're never gonna hit those COPs or EERs or whatever, efficiency standard we're looking at. It needs to run for that to happen.
Right.
So that's really, I mean, when you talk about runtime, we're always, even with the DX system, we're out trying to challenge contractors to get these things sized correctly so that they run longer, especially with our inverter driven compressors. When they're running longer, they're performing better. They're using less energy overall than they are stopping and starting. So it's interesting that air to water does the exact same strategy.
That's right. Yeah, you think about it, right? The refrigerant could be the same, the compressor could be the same, right? The basics of refrigeration is still the same. The only difference is that we're converting it into water. And typically it's going to be a propylene glycol and water mixture for most areas that have that's obviously going to be prone to freezing. But that fluid and the principles of heat transfer are still the same. That fluid has to accept those BTUs and then transfer them into the house to deliver them. And so you got to make sure that it's very much upon the proper design and application of the product to get it to work right. And that's one of the Achilles heels with air to water heat pumps, is that you do have to put your thinking cap on and do a little bit of math just to make sure that you get the right sized outdoor unit, like you would with the main OJ, right? Your load calculation, that process is still the same, but you got to get that load calc right. You got to size that heat pump, and then you got to size the distribution of the system inside the building. And so, you have all these different tools in the toolkit when you go out to hydronics, right? You can go with radiant floor heated systems. You can go with fan coils. You can go with high sidewall cassettes. You have almost every option you have for DX, with a VRF approach. You have almost the exact same situation with hydronics, if not more, right? Because you can't do radiant floor heating in a traditional DX arrangement, but you can do that here. So so I think there's more kind of tools in the toolkit to pull from, but there's also more things to go wrong. So you got to make sure that you got to do your homework to make sure that we're picking the right size emitters and terminal units inside the building, matched up with the load of the building and obviously the outdoor unit.
Emitter, is that a fancy word for an indoor unit?
What was that?
Is emitter a fancy word for an indoor unit or deliverable? Right. Okay.
Yeah.
Thanks.
Yeah, we call them emitter. In a heating dominant climate, we call them emitters. Heating emitters. We're trying to emit the heat. But you're right. In an air conditioning dominant climate, what the heck are you talking about, right? But yeah, fan coil units, radiant floor heating. These are all different ways of just moving heat, and they all have pros and cons to them. But yeah, heating emitters, cooling emitters.
I want to go back to a strategy in the South. I can remember growing up in Florida as a kid, and we had prior to heat pumps, in the West Palm Beach market, we were using straight cool electric heat systems, right, with minimal electric heat because we're 3,000 hours of runtime in cooling mode. We had these heat recovery boxes. So basically, they were copper coils that the hot gas refrigerant lines circulated around. And every time that the air conditioning system was making cooling, obviously it's circulating this hot refrigerant, which was heating the water that was going into our hot water tank. In essence, my family, 4 children, mom and a dad, family of 6, we had our hot water heater unplugged, if you will,
Right.
Right. During the cooling cycles. Is that what we're doing here with an air to water heat pump? In essence, we're heating that loop of that storage tank, and then that's emitting to the spaces.
Yeah, I mean, it's basically kind of in a nutshell. Like, what I think about for every building in most parts of the country, we need heating, space heating, we need space cooling, and we need domestic hot water. And the air to water heat pump can deliver all three, right? It can produce domestic hot water. And so we always do that. If we're applying air to water heat pumps on a project, let's say on a typical house, that air to water heat pump becomes that first stage for heating the domestic hot water. And we use that buffer tank to kill 2 birds with 1 stone. We use it to heat the domestic hot water through a coil, right? It's like an indirect hot water tank. We call these reverse indirects. We can get into what that means, but basically that tank becomes a 2-for-1. It gives a space heating buffer, gives us that accumulated that volume that we need of buffer storage, but it also allows us to heat the domestic hot water for that home. Then you take a step further and say, all right, well, guess what? We can use that to now heat the house, and we can also flip a diverting valve and go to cool the house. Right. So that's what we're doing today. And that is, that's tried and true. That works tremendously well. And we've been successful with that for many years. What's coming is heat recovery with air to water technology. And so that is where you can run your air conditioning and you can produce the domestic hot water at the same time. So think about this, right? When I'm air conditioning, I'm moving heat from the house and I'm normally rejecting it outside. That's a traditional air conditioning process. So now, instead of just rejecting that heat to outside and wasting it, what if I could take that and dump it into my domestic hot water tank? And so there's some new technology and new companies that are coming on the market that are exploring that further and taking it a step further. But now I can do heat recovery just like I have in any VRF system, simultaneous heating and cooling. The only difference here is that I'm heating my domestic hot water tank when I'm space cooling my building. So if you have a demand, if you got a family of 4 or 5, bunch of young kids, a lot of domestic hot water use, guess what? When you're got that peak air conditioning cooling load happening, sun beating down to that house, I take all that energy and I dump it into my domestic hot water tank. Like it's a perfect synergistic way to get cooling and domestic hot water all happening at the same time. So that's where we're headed with the newer refrigerants and stuff like that, which we could talk about.
So I can tell you, new construction in the early to mid 80s, every home in South Florida had that heat recovery box spiked into the refrigeration or to the air conditioning system, 100%. And then that was obviously those are R22 systems, and HC or whatever they were. As we moved to higher efficiency systems, that technology went away because of from what I thought was the lack of waste or the reduction in waste heat created by, more efficient pieces of air conditioning equipment. It's here, now we're going to be able to go back. These systems are obviously much more efficient than 1985 or 84. Mm-hmm. So, but we're able to capture heat now with this refrigerant and use it just like we did back in those days. Interesting.
Yeah, what's old is new again, right? But we're doing it completely differently than that system that you kind of outlined. But the fundamentals, it's the same concept, it's the same concept. The physics doesn't change. We just have to have the ability to do it with better refrigerants, with better compressors, with better, coils, with better design, so we can get the efficiencies up. But yeah, that's the idea. Move that heat from the building, put it in your domestic hot water tank. And so this will come in with proper sized domestic hot water tanks. So you're not going to have a 40-gallon electric water heater to make that work well, right? You're going to have either a preheat tank, or you're going to have an 80-gallon or 120-gallon, domestic hot water tank. So it will come with some changes to the way we typically design and install systems for houses. And so there'll be an educational part to this, which is why one of the reasons why we're doing this podcast is just try to get the wording out there that these systems exist, and this technology is here, and what all these cool stuff that we can do with it, right? Why wouldn't we want to do that? So it's great stuff.
Yeah. And I mean, definitely we can do a lot of really cool stuff with it, make a pretty complex system out of it. What can you do with an air to water heat pump on a little bit more simplistic level? Maybe a retrofit to a home that's got a conventional split DX system. What are some of the advantages? Does it make sense? Is that something you would look at exploring, or is that not a good application?
Well, yeah. So I'm in Boston, so we do a lot of projects here in the Northeast. And one of the very most common ways that we apply air to water technology in a retrofit strategy is we're supplementing the boiler system. So most houses have a boiler, could be oil, propane, natural gas, and those systems are providing the space heating and the domestic hot water from a fossil fuel approach. The incentives, the rebates, the basically everything's aligning with electrification. And so how do we get electrification correctly into these older buildings? And a lot of these older buildings aren't going to have the capital up front to do a deep energy retrofit. So getting the air tightness, getting the insulation layers, getting that building load down is actually really, really hard, especially on an 1860s built home that's all brick, that we see in a lot of these projects. So we can do the best that we can with that type of project. But what are the other ways that we can handle that? One way we do that is with air to water. So the air to water heat pump can be installed to provide all the cooling for that building. and can be sized to provide the domestic hot water and the space heating preheat. And so the way I think about it is that when it's milder out, the air to water technology can handle the heating of that building, no problem. When it gets to minus, 8 outside, the air to water technology is not going to be able to produce the water and the BTUs that that house needs, right? Because the load is so big that a 5-ton heat pump is just not going to be able to surmount, and overcome that type of load. So if we can't get the air tightness down and we can't get the insulation up on that building, we do it with dual fuel hybrid approach. Dual fuel, meaning we're heating the house with electricity with the heat pump, and we have the ability to bring on the backup boiler when we need to, when it gets cold out. And so we're trying to find that economic balance point. At what point is it better to run the heat pump versus run the gas or propane or fossil fuel boiler, oil boiler, whatever it may be? And that's going to be dependent on your electric rate compared to your utility rates, right? So we're putting these two systems together with a controller that becomes the brain to decide, hey, am I bringing on the heat pump or am I bringing on the boiler? And that's going to look at outdoor temperature. That's going to look at your electric rate and utility rate differences that have been programmed in to that controller, and look at the space heating supply water temperature that it needs to deliver to the house to meet that demand. So it sounds complex, and it can be complex. What we're trying to do is we're trying to simplify it to allow these retrofit houses to kind of reap the best benefit, to get the most bang for the buck by putting in a dual fuel hybrid system. And I think that's where air to water is going to shine in a cold climate. And in other projects that aren't heating dominant, that are more cooling dominant, you can retrofit these in. The challenge there is that these run typically with PEX piping. So you have to have the ability to snake the PEX piping from wherever that piping comes in, basically into the fan coil units, wherever those are located in the house. So there can be a little bit of disruption inside the home to get those PEX lines. No different than if you were running a new line set. Same right. Concept.
So I guess to back up just one step for a couple of the guys that may not have much familiarity at all with this, if we have an existing split system, am I right that we can remove the existing air handler, furnace, whatever's up there, put in a water fan coil, hook up to the existing duct system? You're going to change the line set out for some PEX pipes, and essentially that's all you have to do.
Yeah. Instead of running a liquid suction line to that air handler, let's say in the attic, the difference is that we got two PEX lines, a supply and return line going up to the attic, new fan coil unit that's got a chilled water, hot water coil inside of the unit. So basically a large evaporator coil with a nice, primary condensate pan underneath it, collected condensate, no different than it was before. And they connect to the ductwork that hopefully is good in good condition, good size, et cetera. So we still have that challenge in a retrofit, solution. We want to run some static pressure, just make sure the ductwork is good and make sure it's decently sealed. But yeah, you could just retrofit that in no different than you would in any real TX retrofit and upgrade.
Well, so I sit here thinking about, what Philip and I do on a day-to-day basis for a living, and our interaction with builders and their cries to us for help with labor and things like that. What I hear, here's what I'm hearing. Okay. I can hang a fan coil and run PEX plumbing, right? And connect it to a refrigeration circuit. So maybe there's an opportunity for me to, use the contractor to help me with the design and the sizing and all that. But maybe I can move to a less skilled, more economic installer to run PEX and help the cost of my new home that I'm building by using a different labor pool, if you will. Thinking out.
I love the concept. Think about it, right? Like when you self-contain the refrigeration process outside the building, like you would buy a refrigerator, right? Like a refrigerator, self-contained refrigeration circuit, like that is self-contained. When you buy a refrigerator, you don't hire an HVAC contractor to go check the trim charge or to check, bring it down to 300 microns, make sure that it's leak tight. We don't do that with hermetically sealed appliances directly from the factory. We don't do that. Right. The same analogy could be true with air to water. So now you have that self-contained refrigeration system outside. Now it's water piping. It's PEX, it's copper, it's polypropylene, it's whatever real piping you want to use. And that comes with a lot less in terms of getting it right. Like if someone screws up a flare fitting, that's a small leak or potentially a large leak over a large period of time. if you screw up a PEX fitting, that's one, not hard to do. But even if you did that, you got a water leak right there. You know what I mean? You'll know it right then and there. And you can run these PEX lines can be ordered pre-insulated and in rolls of 50, 100, whatever you need. So you could literally have it be one roll, comes off a spool, and run it up the building, run it inside, run it through the building, cut it at the either end. So there are actually no joints in the entire length of pipe from one point to the other. And it's regular PEX fittings. Like, you know what I mean? So you're right that it's not, you're not dealing with 600 PSI of pressure. You know, you're dealing with 15 pounds of water pressure, you know, like it's apples and oranges, you know, from that point of view. And that's one of the reasons why I love it, right? I don't have to get out my refrigeration gauges. I don't have to tap into the circuit at all. Yeah. You know, if I want to expand, add another zone, cut in, expand it, easy. I don't have to go back to the drawing board and figure out how much 410 am I adding, how much, you know, R32, 434B am I adding? None of that stuff. It's expandable. Just like, think of it like plumbing. If you're running a hot water pipe and a cold water pipe for domestic water, run into your shower, guess what? If you want to add another fixture in that bathroom, you're cutting into that and you're expanding off of it, right? Like you don't need to go back to the drawing board and run a whole new set of home run pipes or get into all that stuff. So if it's designed and installed right from the get-go, you know, that thing should be future-proofed. What kind of formwork area corrosion do we have to worry about with PEX piping?
None.
None. Right? What type of degradation do we have to worry about when, you know, oxygen gets in the system, you know, or someone doesn't use, you know, a proper brazing technique with nitrogen or whatever, right? We don't have those issues. So it should be easier to deploy with this type of technology than we do with traditional, you know, split, you know, DX systems.
So what I'm hearing is a little bit more on the planning side, but a little bit easier on the execution side for the actual installer, less potential for error. Yeah, like you said, right. No leaks. I mean, I've never met a contractor that hasn't griped about Refrigeration leaks. You know, it's just my guy didn't braze it right, I didn't flare it right. You know, there's always something that's causing that refrigeration to leak out over time. And like you said, with the sealed system, and now with the new refrigerants moving towards, you know, mildly flammable, which we've talked about that, and, you know, not anything to be scared of, but, you know, the less we can have of that in our homes. And if we do ever move beyond R32 and 454B, if we ever do move into A3 level refrigerants, you know, that becomes a significant concern at that point. But Ross, I'm in the South, Terry's in the South, I'm in Georgia. We have a lot of humidity down here, and my understanding is that air conditioning, cooling with water-based coils, water systems has a lot of advantages. Maybe you can share some of your experience. Obviously, I know Boston gets plenty humid in the summer, so, you know, humidity removal's a big deal for you guys, but it's probably one of the biggest focuses down here in the South. But what can you tell me makes it different or better?
Yeah. So, there's a couple things to think about here. Right? So if I have, if I compare it to a traditional split system, right, we're really focused on the SHR of that system, right? The sensible heat ratio. How much of that tonnage is going to be, you know, dropping the latent load, dropping the moisture load versus how much of it drops the sensible load, right? So I drop the temperature, I drop the moisture load, and there's a split between that with sensible heat ratio. As manufacturers, no knock to LG or any other manufacturer out there, but the industry trend is to get to higher and higher efficiencies. And to do that, there are some compromises that on the manufacturing side you have to do. And so you can adjust the temperatures of the refrigerant in the coils, you can adjust coil sizes, you can adjust airflow, right? You can adjust compressor ratios, you can adjust those things to drive your SEER2s or SEERs up or HSPFs up, et cetera. Your sensible heat ratio is one of the things that gets lost in that kind of compromised position. And so we might have a system that has a sensible heat ratio of 0.93 or 0.96, right? And so what that means is that out of my 2-ton air conditioner, only 93% of it actually drops the temperature. Only 6 or 7% of it drops the humidity. And so they have to run long cycles. They have to run for 12 to 14 minutes minimum before you start to get any water vapor, water vapor condensing on that coil, right? So it takes a while of runtime, and you don't get a lot out. So think about that as the challenge that we're faced with today. Flip the script, now go to air to water. With chill water, I can run chill water at 41, 42, 43 degrees, obviously well below dew point, right? And I can put in very large coils, multi-row deep coils, right? So these could be 4-row, 6-row deep coils. And in these coils, we can have a very continuous temperature of 41 degrees across that coil. That's going to do an amazing job of wringing out moisture, right? As soon as that coil gets hit with that 41 degrees, we're going to start to see moisture dripping off that coil. And then it can run as adjustable as we want it to be and as long as we want it to be. So we can change that, the water temperature going to the unit to adjust how much moisture it removes, right? So if we just want sensible capacity, we can actually throttle that temperature up. If we want more moisture extraction, we can throttle that temperature down. So we now can do what commercially they've been doing for probably 100 years at this point, which is adjusting the hot water and chill water temperatures to get the proper dehumidification that the system needs to deliver. Right? You still have the laws of physics. You still need to make sure you have proper airflow going across the coil and all that good stuff. But guess what? We don't have to worry about the risk of freezing up a coil. The icing up of a coil or evaporator becoming an ice block, that's not a thing in chill water. We don't have that concern. So the whole 400 CFM per ton or 350 CFM per ton, it's baloney now. You could go to 200 CFM ton. You could go to 150. You could go to 100 CFM a ton.
Yeah.
You could just let that water vapor just drip off that coil. And, obviously you're just going to get an unbelievable dehumidifier when you do it that way. And so we can adjust airflow, we can adjust the water temps. And we really have, and if you really want to take a step further, you can go chill water coil, hot water coil. So now you can do reheat. So you can do chill water coil, knock the moisture down, reheat the air back up with the second coil. And guess what? Those can be tied to the same system.
And what that makes me think of is one of the big struggles for typical DX systems is shoulder seasons, right? So, and we're in it right now. Is 82 degrees yesterday here. It's 67 degrees today, but muggy and humid. And my air conditioner just isn't going to have enough runtime. I can't set the airflow slow enough to really have it run long enough to take the humidity out of my home like days like today. So a lot of the builders are adding in dehumidifiers for shoulder seasons, which is great. And I'm not saying that this would necessarily replace it in every circumstance, but it seems like in the shoulder seasons, we would have the ability to chill the coil down, slow the air down, not overcool the home, but just like you said, just let that thing wring out moisture and barely flow that air across the coil nice and slow and not freeze the house out, but really dry it out.
That's right. That's right. Yeah. Just think about a low airflow, tremendously low airflow going across that cold 41 degree coil and let it run and run and run. And so you're going to have very little difference in temperature of that space, but you're going to have nice dry air coming out through that supply. And then of course, as that hot, humid air goes through the return, the process repeats and it just runs low and slow. And then, if you want to, you can get into reheats, right? So we can reheat the air back up. And part of that's going to be dependent on application, right? How airtight the house is, what does that infiltration look like? What's the loads look like? But you have that ability that you didn't have before with DX, with traditional DX.
Huge.
What,
Huge.
what do we see for the development of, here comes this word, emitters? What, do we see new fan coils being created? Do we see new ways to deliver this amazing technology in a residential application? Like you said, it's been a commercial applied product for a long time, but man, I got to tell you, I'm excited about what I'm hearing here.
Yeah. So you got all the same kind of traditional means and methods that you have now, right? So you could go with a package concealed unit, like your slim duct unit, right? And you could have, your ductwork coming off of that. It could be a chill water coil in there. It could be chill water, hot water coil in there, depending on, the setup. And it could be an ECM motor, variable speed, and so very similar to what's already being done. Those products exist today in the US market and we're using them. There's a bunch of products that we are toying with and we've played around with that are new to the scene. One of those is called a trench heater or trench cooler. So think about this. Think about you got a big glass facade, with big nano walls, sliding glass doors, whatever in a house. And let's say it's down the south, huge solar gain loads, right? Big load coming through that glass. What if I could put a trench box, let's call it, think of it as almost like an emitter, a coil sitting down in that box with little fans on it that can pull air from the room into it, go across that coil and blow that cool dehumidified air across that glass.
Well,
So almost the exact opposite we would do with like a linear slot or linear bar grill coming from the ceiling, blowing, cool air, dehumidified air across that glass from the ceiling. We could do it from the floor. And now what I have the ability in that trench that it sits in, it actually collects condensate and is draining condensate down and away. So this is common in Europe. They do this a lot in Europe because a lot of the houses in the Northeast and in Europe are similar, that they have basements. So we can address it from below, and that's where the piping is coming from. So now I can heat that air or cool that air, and I can dehumidify that air, and I can do it all with no ductwork. It's self-contained. And so we're doing a project right now with that exact product. And so there are new emitters that are coming to the United States that are just basically being adapted from the Asian markets and from the European markets and bringing them over. So I'm excited about that.
Great stuff. Philip, anything else for Ross before we let him go out and design some really cool stuff?
Yeah, I mean, it just kind of is opening my eyes to what I don't know. You never know what you don't know, and there's a lot. Just thinking about the different emitters that potentially could come, because, like you said, you can take as little or as much water as you need out of these systems and make smaller zones. And good gracious, there's just so much potential. But I guess from the simple side of things, I mean, I know we can make some really elaborate, really amazing systems, but we don't have to. I think that's one of the things that really hit me, is just that if I have a house that's using a single zone DX heat pump system, I can do the exact same thing, just do it a whole lot better if I'm using water. And to me, that's just like, if I were a contractor still sitting here in Georgia or Florida or wherever, I would go, I want to learn how to do this because nobody else is doing it in my market.
Right.
I don't know of any contractors in this area that are pulling out DX systems and offering this as a change out, or to their builders that are building higher end homes going, hey, do you want to do the best? Do you want to do something different than what everybody else is doing? To me, that was kind of my biggest takeaway right there.
Yeah, we see a lot of contractors in our market that are differentiating themselves. And that's one of the ways that they're differentiating, is they're becoming the air to water kind of gurus that are saying, hey, we can do the traditional stuff, but we're going to also have the option to do this. And here are the pros and cons. And there's usually a price premium for it. But if the homeowner's on board, then it's a slam dunk. And they become that go-to person for them. And they do a great job. The other thing too that I'll mention real briefly is that we're potentially going to be moving to A3 refrigerants. And so when we go to A3s, those are highly flammable. That's like propane, like R290. And so guess what? If that happens, I don't have to run new line sets. I don't have to get into the building at all. I can literally just take off the box that's outside the house and replace it with a new box. So now I'm just box swapping, just take off the R32 unit, bring in the R290 unit, plug it into that, piping that's there with the propane glycol water mixture, pressurize, and then off we go. So, that's where I think we're going to start to future-proof these buildings by doing it this way. But I'd be hard-pressed to also mention the cons of air to water. I do want to mention a couple cons.
Please.
For one, you're running chill water at 41, 42 degrees in these buildings, maybe 45 degrees. With that is you're below dew point. So you got to make sure that every bit of that PEX pipe is insulated and vapor sealed, right? So that's one of the things that we always tell our contractors that we work with, get the pre-insulated rolls of, it's basically like an EPDM closed cell elastomeric foam already wrapped on the PEX pipe. So it's continuous, it's vapor sealed from end to end. That's one thing that's important to have from the get-go. You don't want to have one that has a seam that allows the, humid air to get in there and let condensation form. That's one thing. Other thing is that it does require a little bit more indoor space, because these systems are going to have an expansion tank. They're going to have some circulator pumps, at least one circulator pump. There's going to be the hot water buffer tank or, domestic hot water tank. And there's going to be, a couple of small items like that needs to find a home. So there's a little bit more space that's required with this system. And yeah, I'm just trying to think if there's any other big negatives or concerns. I have, if you're snaking the piping through, I know that pre-insulated PEX can get snagged, just like if you're snaking a line set through. So that's one thing that's, pay careful attention to when you're snaking it through. But you think about all the future proofing capabilities, you think about all the pros that we talked about. and then you add in the time of use rates that are happening. Now I can pre-charge the system, and run that cooling or heating ahead of time when electricity is cheap. And then I can roll it in so that it goes into coast mode. So think about it, if I have a buffer tank, I could charge it, let's say cooling dominant in your market, right? We charge that tank up at nighttime when power's cheap, charge it up to 41 degrees, let the tank sit there. And then guess what? All throughout the day, now I can just pull off that tank. I don't have to run my compressor. So you think about
certain markets where their power drastically changes price.
Yeah. Time of use. Good stuff.
Yep. So yeah, a lot of good things, a lot of good features there. Obviously pros and cons with any decision, but yeah, I think air to water is here to stay.
Ross, we don't want to cut it short here, but I want you to talk a little bit about, or just at least mention, what you do for a living and how can folks reach out to you? Let them, you're a wealth of knowledge. Let them know how to get to you.
Well, yeah. So I run a consulting engineering firm in Boston called TE2 Engineering. So you can find us on Instagram. You can find us on all the social media stuff and our website, te2engineering.com. And then I'm also on the television show This Old House as their building engineer. So that airs on PBS periodically throughout the year, as well as on Roku and different digital streaming platforms. So you can find me on there as well. But I'm also on social media. So Ross Trethewey or Ross Tret, depending on which social media platform you're on. But yeah,
awesome.
That's where you find me.
Awesome, great. Well, Ross, we want to thank you for jumping on here with us. Certainly you're a wealth of knowledge.
Yeah, well, thanks for having me. I love talking about this stuff. Obviously, thank you for what you guys are doing with the industry. It's a rising tide raises all boats, right? So we're doing some great stuff out here.
Awesome. Well, again, thanks for your time. Thanks for joining us. Everybody out there, thanks for joining us for this episode of the LG Procast, and we will see you next time.
Bye-bye.
This episode of the LG Pro Podcast was recorded by LG Electronics USA Inc., LG, and features a discussion between LG hosts Terry Frisenda and Phillip Kriegbaum and Ross Trethewey, principal of TE2 Engineering, about water heat pumps. Companies mentioned in the podcast, TE2 Engineering and This Old House. LG is not affiliated with these companies and does not endorse their products or services. LG disclaims all liability and is not responsible for any damages or issues arising from the use of this company's products or services. LG and the LG logo are registered trademarks of LG Corp.